Welcome to Wonderfest 2008, the 10th anniversary of the Bay Area Festival of Science. My name is Norm Sperling. I'm the Vice Chair of the Bay Area Skeptics and the editor of the Journal of Irreproducible Results, the Science Humor magazine. I'll be your host and moderator. Well, thank you. I'm hosting this first program. For the next 90 minutes, we're going to explore, does anything happen at random? But we're not going to explore it at random. Instead, we have an orderly way of doing things, well, semi-orderly way of doing things. Our two speakers will divide their time between them, and they will each present a case kibitzed by the other, and then we'll open it up to the audience for questions. Before introductions begin, I'd like to express our gratitude to the Stanford Chemistry Department and its chair, Dick Zare. Is he here? Well, we thank him anyway. What? The department's been very generous and hospitable in hosting Wonderfest here at Stanford. Wonderfest's mission is to make science and scientists accessible to the public. Together, Stanford Chemistry and Wonderfest bring that mission to life each year. Don't forget to pick up your official and personalized Wonderfest Truth Flirter ID card, sponsored by Picturoo.com, in the lobby. This card, personalized with your photo, signifies that you are our official Wonderfest Inquisitor. Proudly wear it to show that you have been flirting around here. Our speakers this afternoon are Persi Diaconis and Daniel Fisher. They're both professors here at Stanford. Dr. Diaconis is a professor of mathematics and statistics. He has a lifelong interest in randomness and deception, though he promises not to deceive us too much. He's one of the co-founders of CSICOP, the Committee for the Scientific Investigation of Claims of the Paranormal. Dr. Fisher is a theoretical physicist here at Stanford, formerly from Harvard, but he learned better. He's interested in understanding the effects of randomness in physical systems, and he's also interested in the dynamics of evolution. Now, have you two agreed on who's going first?
I am.
Persi is going first. Okay, Dr. Diaconis.
Thank you very much. Hello. I'm amazed that so many people came in from the rain to hear about what we're going to talk about. We'll try to make it as good as we can, but I need your help, so pitch in if you have an idea or a question, and I'll remind you. So the issue is anything random? And that one could talk about that forever, sort of as philosophy and as many, many other things. I'm going to talk about it in a very down-to-earth way with two examples. And the first, and we'll see if this thing is in focus and how it goes on. That's it. So there's an image of something, of random, which is if you had a deck of cards, here is one, and how many times do you have to shuffle it up to make it random? And everybody has an intuitive feeling of that. By shuffle, I mean what you mean by shuffle them. And of course, if you do it once or twice, probably it's not enough. And if you do it 1,000,000 times, probably it's enough. And how do we talk about that and how do we think about it? And that's a kind of example that we can get our hands on and then use it as a springboard to talk about deeper things. So suppose you had that problem and you wanted to try to think about it. There are a couple of cases that you might begin with. If I had a tiny little deck, 4 cards, and I had some well-agreed-on method of shuffling, I was going to give them to my kid and say, mix them up. And, well, if there were only 4 cards, there are 24 ways in which 4 cards could be arranged. Any of the 4 could be on top. Any of the next 3 could be next. Any of the next 2 could be next. So 4 times 3 times 2 is 24. And you could imagine actually trying it out and see if it works. Put the cards in order. Say they were called 1, 2, 3, 4, and then, let the kid shuffle them a few times and check what order they're in. Do that whole thing a lot of times and then see if each of the 24 orders occurs about equally. Then you'd say, okay, they're random. Or if some orders don't occur, you'd say something's wrong. So with a little deck of cards, it's pretty easy to think about the question, how many times to shuffle them up to make them approximately random. Now, that's good. That's a good basic image to keep in mind. Suppose now there were 52 cards. Well, there are more arrangements of 52 cards than of 24. In fact, the number of arrangements is something like 10 to the 68th, which is more than the number of particles in the universe. And when people hear that I study shuffling cards, they say, well, can't you do all of that stuff on a computer? It's nice to know that there are some things that you can't do on the computer. If all the atoms in the world were little computers all working together, never once will they go through all arrangements of an ordinary deck of cards. So you can't use that brute force method. Try it out, and just see whether it's about equally likely. So what else could you do if you wanted to think about this question, how much to mix things to make them random? Well, another thought you might have is to make some test. That is, you might see some features of the deck of cards. I'm thinking of the deck of cards starting out in order, and you know the order, and then you want the order to go away. So it might be that you might, the king of spades is on top, and you ask somebody to shuffle a deck of cards 4 or 5 times, and you could see, is the king of spades still near the top? So you could make various tests. But that would never be completely satisfactory because there's all kinds of tests to think about. Okay, so what I'm going to introduce is a third method. I can't try out all the possibilities, and I'm not so happy with the tests. So here's a third method, and let me now start to say what some of the words will mean for us for the next few minutes anyway. In order to discuss this question as any part of science, you do have to say what you mean by shuffle and what you mean by mixed. So what I mean by shuffle is you cut them about in half this way, and then you shuffle them the way you do. And we'll make a more careful mathematical model for that as we go on, but everybody has some intuitive idea of what I mean by shuffle. What I mean by mixed is all arrangements of the deck should be equally likely. So all n factorial, and with 52 n factorial, I said it's about 10 to the 68th. All of them should be equally likely. So how do I write any of that down? Well, I write the uniform distribution, u of pi. Pi is an arrangement of the deck of cards. The uniform distribution is 1 over n factorial. That is, every arrangement of the deck should be about equally likely. And we have some mechanism for shuffling, and I'll discuss it more carefully when I need to, but I'm calling it P of pi, and that means, in whatever mechanism I'm talking about, what's the chance that the deck is in the arrangement pi after one shuffle? That's one shuffle. Of course, we want to talk about iterated shuffles, and so that's at the bottom line there. What that means, those squiggles mean, is what's the chance of the deck being in arrangement pi after 2 shuffles? How could a deck get in some arrangement after 2 shuffles? You had to have done something your first shuffle and then made the shuffle that brings you to the arrangement you're interested in after a second shuffle. So that's that formula, it's called convolution in my part of the world, is the chance that the deck is in the arrangement pi after 2 shuffles. And similarly, you could, if you knew if you'd specified a way of shuffling, you could say, in theory at any rate, what's the chance that the deck is in any given arrangement after any number of shuffles? Now, so that's what I'm going to mean by shuffling, and I'll be a little more careful in a second. What does it mean by close to random? I'll try to explain this in English, but there it is in gobbledygook. So that left-hand set of symbols, the distance between a deck shuffled k times and the uniform distribution. And the definition of that distance is the right-hand gobbledygook. And what that means is the following. Take any set of arrangements of the deck that you can think of. I call it A. A might be, for example, the set of all arrangements where the ace of spades is in the top half. That's a set of arrangements. Or A might be the set of arrangements where the king of hearts is above the queen of diamonds. Take some set of arrangements. Look at the chance that the deck is in that set of arrangements after K shuffles. Look at the chance that the deck is in that arrangement if it was perfectly shuffled. Take the difference between those two numbers, and then take the worst case. Take the question A, which makes those two mechanisms as far apart as possible. That's a notion of how close to mixed up a deck of cards is that in principle you could think about and do math on. With those two things specified, namely given a mechanism for shuffling and this notion of how mixed up we are, I can now ask a well-posed math problem. That informal question I began with is now a well-posed math problem. Given a challenge number epsilon, maybe it's a 10th or a 100th or 1 over 10 to the 68th, given a challenge number epsilon, how large does K have to be? How many times do you have to shuffle so that the distance from random is less than epsilon? So that translates an informal question into math. Now, before I go on, I'm going to ask a question that we very rarely allow ourselves to ask in public. Who cares? Everybody knows that if you shuffle a deck of cards 3, 4, 5 times, they're all mixed up. Well, just like many other things that everybody knows, it's just wrong. That's all. I mean, just wrong. Wrong, wrong, wrong. So how can I explain that to you? Well, I'll explain it to you this way by teaching you a card trick. The card trick goes this way. Tucker, our fearless leader, is wherever he lives. Where do you live, Tucker? Corte Madera. I know where Corte Madera is. That's not so far from here. But anyway, you're in Corte Madera, and I'm home here. And you get a letter from me saying, "Dear Tucker, it was great to see the Wonderfest audience. By the way, I thought you'd like to see a card trick. Noticed I've enclosed a deck of cards with this letter," and the letter has a deck of cards in it. Okay, would you take the deck of cards out of its case? Okay, he's home. I'm not around. Give the cards a cut. He cuts the cards. Give him a shuffle. Okay. Give him a cut. Cut. Give him another shuffle. Okay. Give him a few more cuts. Cut, cut, cut. I'm sure you'll agree no living human could know the name of the top card. Now that sounds right. I mean, you are home and you don't know the name of the top card, and I'm not there, so okay. Take that card off, look at it, remember it, and put it back in the middle of the deck. Okay. Give the deck another shuffle. Give him a few more cuts. Mail me back the deck. Oh, yes, and at 7 o'clock every evening, concentrate on your card. And in a few days, or however long the mails take, he gets a note back saying it was the 7 of diamonds. And it was the 7 of diamonds. Okay? It not only says it was, right? Okay, so that's a trick. And my magic friends hate this part, but anyway. How does such a trick work? Let's discuss that. Okay, so the deck I send him is arranged, and for purposes of this discussion, suppose it's ace of spades, 2 of spades, 3 of spades, etc. In fact, he's a clever guy. He might look at the cards before he starts following instructions, so I might just shuffle a deck and write down the arrangement. Anyway, I know the arrangement of the deck of cards that he's got. Okay. Now, when you shuffle a deck of cards once, why isn't it random? So here's the physics of shuffling cards. Well, what do? You cut the cards in half this way, and you do something, right? I don't know, something. You interleave them some way, right? So why isn't that random? Well, the top cards, the cards in the half that you cut off, stay in the same order, and the cards in the bottom stay in the same order, right? That is, these cards, if you shuffle, you know, this is above, this is above, this is above this. However you shuffle once. Okay, so the deck has 2 rising sequences. I'll explain in a second. I wish I could do this part, but I can't. Now his second shuffle. So he cuts the cards off, but this top half has two rising sequences, right? Because they're kind of interleaved, right? The top half has two rising sequences. The bottom half has two rising sequences. When he shuffles them the second time, there are four rising sequences. And after the third shuffle, there are 8 rising sequences. When he takes that top card off, puts it in the middle, it makes a 9th rising sequence of length 1. So what do I do when I get the deck back from him? I just start to play solitaire. I turn up the cards. There's the 10 of diamonds, okay? Next card, 3 of spades. If the next card were the jack of diamonds, I would play it on the 10, right? So I start dealing the cards into piles, and if one card follows the other in the original order, I put it on the pile. Otherwise, I start a new pile. So the next card, 10 of hearts, it goes into a new pile. What you'll find if you try it, and you can try it, is you'll have 8 piles, each about an eighth of the deck. You're undoing those 8 rising sequences, and a 9th pile of size 1. So what you can conclude from that is that shuffling a deck of cards 3 times is not enough. Well, similarly, shuffling a deck of cards 5 times isn't enough. If you track it through, after 5 shuffles, you can have at most 32 rising sequences, and that misses a large proportion of the possible arrangements of the deck. And I call to your attention that so far, I don't care what mechanism you use to shuffle the cards. You can shuffle them perfectly, you can shuffle them in a clumpy way, you can cut cards off and just put them on the bottom. However you shuffle cards, if you shuffle them 5 times, you're missing a big proportion of the arrangements. It's not random. In order to go further, I need to make a more careful mathematical model, and I didn't need to make it. Somebody made it for us. It's Ed Gilbert and Claude Shannon at Bell Labs, and Jim Reed's also at Bell Labs. They introduced a simple mathematical model for shuffling cards. I'll just explain it in the air. It's written down there. So I cut the deck initially about in half, according to the binomial distribution, a discrete version of the bell-shaped curve. I cut the cards originally in half, and then I've got my 2 piles. If the left hand has A cards, and the right hand, my right, has B cards, I'm going to drop the cards with my thumb. The chance of dropping the next card from this pile is A over A plus B. So you drop cards with probability proportional to the packet size. And then you continue. So maybe you cut them exactly in half to start with, so half the time you drop a card from your left half. Now this has 25 cards, this has 26, so you're a little more likely to drop a card from the big half. It's springier. That's a mathematical model for shuffling cards. And what I did was to do the math of that model, and let me tell you the answer so that you can look and see. So this is the answer for 52 cards. Let me try to explain. These are some numbers. So on the left is how far am I away from random? And K is 1 shuffle, 2 shuffles, 3 shuffles, up to 9 shuffles. Okay. After 1 shuffle, now that number is really 0.99999 about 15 places, but I didn't think you'd care about that. It's 1 to 4 decimal places. After 2 shuffles, it's 1. You're as far away from random as you could be. After 3 shuffles, after 4 shuffles, at 5 shuffles, something starts to happen. It notices the cards are being shuffled. After 6 shuffles, it drops down a little way from 1. After 7 shuffles, it drops by a factor of 2. And then after 8 shuffles, it drops by a factor of 2 further. And that keeps going forever. So I can't tell you how many times do you have to shuffle a deck of cards to make it random. You have to tell me how close to random you want to be. It's never perfectly random. But, you know, so if the honor of the country depended on it, okay, shuffle 11 times. You know what? Okay, if you're playing with your grandma, maybe, you know, 7 shuffles is enough. We won't pursue that any further. But the way I like to code it up is that the cutoff, the transition from order to chaos happens at about 7 shuffles. I won't take you through this, but I'm a math guy, and so we, in fact, of course, with Dave Beyer, a geometer from Columbia, we did this for a general deck of size n, and you can say how many times you want to shuffle, and then we have a kind of formula, which is a very good approximation. A thing to take away from it is that there's a sharp transition from order to chaos. This formula says that too. The deck stays kind of where it is and then drops off very sharply to 0 and by these powers of 2. And if you ever wanted to look, can somebody really write a math paper about shuffling cards? There's one that I wrote, and I've actually written quite a number of them. So where are we now? So I was asking this question of how many times do you have to shuffle a deck of cards to mix it up? I got myself into analyzing a mathematical model of shuffling, and then there's some math to do, and I told you a little bit about the math we've done. A natural question is, this theorem is a theorem that has some assumptions. I'm assuming that the cards are shuffled the way I just said. Is that a good model of reality? That's a different question. It's an important question. And I say yes, and the reason I say yes is that I've asked real people to shuffle real cards, and I've, thousands of times, and I've compared the way they drop cards with this Gilbert-Shannon-Reed's model, and it's a pretty good model of reality. I have one more thing about shuffling cards, and then I'm going to ask for your help, and okay. I've been talking about shuffling cards the way we do it, okay? Now, suppose here's another issue. A lot of people play online poker. I won't ask for who's played online poker. You know who you are. If you look on the web, you'll find a fascinating article called How We Learn to Cheat at Online Poker. Okay. Just look it up. That's the title of it. I'll tell you the story briefly because it does reflect on this story about what's random. So online poker, there's some little office in the Bahamas where some guy has a computer and it generates arrangements of a deck of cards. It doesn't do this, right? It has a sort of little internal random number generator, whatever the computer spits out, and it uses that to rearrange the symbols. Well, some people like me, maybe some people like you, had the idea that they weren't really shuffling. And so maybe you could figure out what they were doing. So let me try to explain some of these numbers. So the number of arrangements of a deck of cards, more carefully, it's 52 factorial. It's 8 times 10 to the 67th, so I rounded that up to about 10 to the 68th. It's a lot of different arrangements. Their random number generator was a 32-bit binary digit generator. The number of different possible outcomes of that generator are 2 to the 32, and that's around 4 billion. So it's a lot less than 10 to the 67. Okay. Now, really, the way the random number generators work is they have an internal clock, and when they're turned on, they look at the number of milliseconds since the start of the day. And they start there, and then they do a deterministic thing. The next random number is the last one multiplied by something. It's just some completely non-random scheme. So really the only random thing is when they start it. And so the number of milliseconds is something like 1 million or a little, 10 million. But really they know also about when they started. They know when the office opens. So they got down to there were going to be a couple of million possibilities. These are kids. And they cracked the random number generator, and then the game was Holdem, which is a game in which you get 2 cards, and then, so you see 2 cards, and then when the flop came up, the 3 cards that show at Holdem, they knew completely the arrangement of the deck of cards. That makes it easier to play skillfully. So the analysis, a point is this. The analysis that I did for physical shuffling doesn't say anything about this. They were people who were skeptical about the mechanism that the casino operators were using to shuffle their cards. They figured it out and they made money. By the way, there's not an illegal twinge in this, right? They were just thinking. They were just, figuring out what the enemy was doing and taking full advantage of it. Now it's illegal to play online poker in the States, so that could well be. So that's a little picture of how a mathematician, statistician, analyzes a very familiar random phenomena, namely shuffling cards. Before I go on about anything, it would be a big help if you would ask some questions. Okay, so are there any comments or questions? Yes? That's that question. I love that question because I know the answer. There's the other way of shuffling, this way, right? Or some way like that, right? That's the way you were saying, right? That way of shuffling. It takes about 2,500 of those shuffles to mix up cards. It's a really inefficient way of shuffling. And a thing that's interesting about it is there's something kind of fundamental about the difference. In my riffle shuffling mechanism, this riffle shuffling mechanism, which is so efficient, it's easiest to explain to you this way. I'll tell you a shuffle is this. An inverse shuffle is you go out. I take some of the cards and it's just the reverse of a shuffle. I remove some of the cards, I put it on top. So it's easiest to picture that way. The shuffling mechanism I told you about, its inverse is like this. You have a deck of cards, you flip a coin for each card, and then you take all of the heads and put them on top. Turns out that has exactly the same math as that I'm doing. So there are about 2 to the 52 different permutations that occur. The model that I was analyzing to answer your question also has the same amount of randomness. The mathematical model was, between each card, I flip a coin. And then I say, you cut off or shuffle off everything up to the first head. Drop those. Then everything up to the second, wherever the heads are, you would drop off some cards, drop off some cards, drop off some cards. So you drop the cards off in clumps, and those clumps, the sizes of those clumps are by where the coins are. So those two methods of shuffles take the same amount of randomness, but one uses the randomness much more efficiently than the other. And so if somebody's shuffling that card, and you happen to want to take advantage of them, you could. Back in the back. Hi, Martin.
What even, Holdem, just put it right in on the table.
So my colleague in electrical engineering is asking a question I don't like so much because I don't know the answer, but I've worked on it for years. So in not only the older method, it's still in current use. If you go to Monte Carlo, where they play Baccarat, before they play Baccarat, they do what I call smooshing. That. I don't know if you can see it, but everybody knows what I'm doing, right? So you can ask, how long do I have to smoosh them to mix them up? Well, I wish I knew the answer. I don't. I have both tried it and I'm working on it currently. No, in the sense that the first question is to get some mathematical model for what is going on. For example, something which would allow me to run the smooshing operation on a computer, just to try to write something like that down. So he's suggesting a model which is something like what I'm using, and this isn't prepared, by the way. We are trying to make some sort of, this hand does some sort of random walk and then carries the cards along with it. It's been very, very challenging to analyze that model. So even a simple variant on a natural problem, it's beyond mathematics as we speak. I did test it because if you wanted to think about, well, suppose you don't do it enough. Why aren't they random? Well, kind of intuitively, you would think there would be cards which were originally together, which are still together. If you didn't smoosh them enough, they would, So that's a thing you could test. That's a natural test statistic. So I did it 100 times. You know, I set the deck up, I smushed them for a while, and then I saw how many cards. And it's pretty effective, actually. It was surprisingly better than I thought. So I don't know the answer, and I'm not proud of it, but that's the truth. Yes, sir.
What happens if you do that first method you described earlier, where you just start with like a few, like 4, and smush 4, and then maybe smush a few more and so forth, that kind of thing, and think of it in those terms? Is that helpful at all?
So the question was, could I build up from the easy problem we were talking about, which is with 4 cards? Probably I could, and we could analyze that problem with 4 cards, and then try to maybe smush another 4 and then put those together in some way. You might be able to make progress that way. I'm still trying to get some simple back-of-the-envelope model that I can analyze, but, well, not unfortunately, the national defense doesn't depend on it, so it's just, it's one of the things I'm doing. Although there's a wonderful James Bond movie, right, in which they were playing cards, and the national defense did seem to depend on it. But no, you can build up. What I thought you might have asked is, what if you combine 2 methods? And again, the math of that is beyond our understanding. That is, if I asked what they do in Vegas, so that's a thing. There's an achievement that'll probably be on my grave. Dave Beyer and our theorem changed the laws in Nevada. Well, that doesn't happen so often. They used to shuffle the cards, 4 or 5 times, and now by law they shuffle 7 times, and they do 2 of these strip cuts, the ones you were asking about. Well, okay, that's and I don't know how to do the math. It seems quite challenging to combine different methods of shuffling. And so we're happy to have examples that we understand, but it's very easy to ask questions that we can't analyze by math. And then I'm really stuck. The only thing I could think to do would be to smush and then look at the data and try to guess it some way it wasn't random. Just in practice that way. Yeah.
So you described 2 methods of shuffling, one of which use the randomness much more efficiently. Is there a theoretical limit to how efficiently you can use the randomness?
Is it?
So in other words, could you build a machine that optimally shuffles?
So the question is, the 2 ways of shuffling, riffle shuffling and overhand shuffling, as we call them in the trade, use the same amount of randomness, and one is much more effective than the other. And there is the standard theoretical entropy type bound, Shannon's entropy, and it's the same Shannon. And he was thinking about that, and I think the riffle shuffles come pretty close to using the Shannon, to achieving the Shannon bound. That is, there may be a factor of 2 off, but you can also do them. I don't need some fancy theoretical thing. Yes, it's quite close. It's quite close. Back in the back, hi.
What would happen if you, before you shuffle, you take the top 10 cards and you simply reverse their order, then do the shuffle? You do that each time you do a shuffle.
Right, so it takes some, that problem not only could I analyze, I did analyze. Susan Holmes and I I get a lot of funny notes because I give talks like this, right? We got a note, a letter, and it was from a company called Shuffle Master. Oh, I said, Shuffle Master, that sounds interesting. And I open it up, and it's a letter, and it says, I'm the president of Shuffle Master. We are the largest manufacturing of shuffling machines in the world, and we're often asked, do our machines really work? I am a mathematician, I have a PhD, but I don't do that kind of math. You do? Would you come talk to us? Oh boy, would I. So we flew to Vegas, and Shuffle Master is on the New York Stock Exchange. It's quite a big company, quite a successful company. And they make machines, and if you go into a casino now, more or less dealers don't shuffle cards. The machine does something. And the machine does something very much like what you suggested. And so because I wanted to get paid, we could do the math of that from the math that we know, and it didn't change things very much, it wouldn't change this 7 shuffles. Their machine had, and many machines now, had 20 shelves. This is actually quite interesting philosophically. Their machine had 20 shelves inside of it. The deck is dropped inside. The deck goes up and down, and a wheel spits off cards onto the various shelves. Okay? A thing is, sometimes it puts it above the cards that were there and sometimes below. So first of all, this machine was just gorgeous. I mean, it was this piece of, like a little vacuum cleaner or something, and it worked. You know, it wasn't going to splutter the cards all over the place. It actually worked. But there was nothing random about it in the sense that the decisions that the machine was making were governed by one of these little silly random number generators that I was talking about before, which multiplies the last random number by 69069 to get the next random number. Almost all of the true randomness in physical, biological sense that I was talking about is being taken out of the casino, and it's all being replaced by these silly little random number chips, which aren't random, and people can go and take advantage of it, and they are. Meanwhile, one of the things we told them is that your machine doesn't work, and they really didn't like that, because they had two. Yeah, they did still pass. You know, he said, it's not the answer we wanted to hear, but that's what we hired you for, and thank you very much, and they did pay. And, because what they did is deal the cards onto these 20 shelves, it's actually 10 shelves, it's 20 because of top and bottom. Deal the cards onto these 10 shelves, and then they output the packets once. They did the whole thing once. And if you see, you know, if you start to think about the way things move around, you could see how you can actually analyze that. And now, there was an interesting problem. How do you explain to tough casino guys, you know, the guys with the cigars, and, right? Trying to explain total variation distance, you know, in these formulas, they just couldn't care less. So, and this is the last thing I'll say about this, and try to switch off. But here's the way we explained it to them. Suppose the deck of cards is really perfectly mixed, and the cards are turned up one at a time, and you try to guess at what they are, as you might if you were playing blackjack or something like that. You want to know what the cards are, but you see them one at a time. Okay, so how well can you guess? Well, the first card, you don't know anything. It's a well-shuffled deck. Your chance of being right is 1 in 52. Okay. Now you throw it away. The chance of being right on the second card is 1 in 51, and then 1 in 50, then 1 in 49, and if you have a good memory, you know the last card because you remember everything that went before. So what does that give you? Well, 1 plus a half plus 1 plus a half plus a third plus 1 in 52, and that's about 4.5 when you add them up. It's log n with an n card deck. So if a deck of cards is well shuffled and you try to guess one at a time, you get about 4.5 cards right. What Susan showed is that with their shuffling mechanism, and because of the math that we knew, but we didn't have to tell them that, you could get about 9 cards right. And they said, okay, you win. That's too much for casino play. I think these questions and the stories give you a fair feel for a sort of pragmatic kind of talk about whether things are random. I'll give a first answer for myself for is anything random? Now, there's all kinds of, is anything, right? Well, shuffling cards, flipping a coin, basic images of random phenomena. My answer is no. And in case after case, and I've just told you about one of them, while if you shuffle a lot, you can get close to random. In fact, we're lazy. We don't brush our teeth enough. We usually shuffle too little. We usually don't flip the coins hard enough. And there really is non-randomness where it matters, at least in this case in the casino, in that you could go to a casino and make money. So many things where people naturally assume that they're random are really not very random, and then thinking people can take advantage of that. But often the schemes are such that they could be made kind of effectively close to random. Thank you. That's my first pick at randomness, and I'm happy to, bring Daniel into this. And unless you want me to start on coin tossing, which I'm also happy to do, Daniel. our perfectly choreographed efforts suggest that I should tell you.
Well, he's having a sip of water, so that one of the messages from this is going to be that physics is much more random than computer science.
Okay. So here's a question. For me, I have to get one of these guys out here. Okay, here's one. That's a dime. For me, one of the most primitive images of a random phenomena is that. Is it heads or tails? It really feels random to me. It's 50-50, and I don't want to discuss it. It's random. Well, is it random? He said. I say, unfortunately, fortunately, coin tossing is physics. So I had the physics department build me a coin tossing machine. And it's a little gadget like that. I'll show you what it looks like. The coin goes there by the thumb on that little piece of tape. And then I'll show a close-up of that. The screw is turned that way. There's this ruler. The coin goes up in the air that way. We must have shot, an hour to get that. See, it's up there, edge on. But it does go. It looks just like that. Okay. No, yeah, but it is. That's right. It's not a screwdriver. It is really the coin, and it's true. It could be a screwdriver. It's not. And then, miracle of miracles, the coin lands in the cup. No, but the point is, the coin always lands the same side up. And the same side as it started. And it's the damnedest thing you ever saw. I mean, it's viscerally very disturbing, especially if you're in my business. You've got this thing, ping, it goes up, boom, heads. 50 out of 50, something's wrong. It just feels wrong. But of course, coin tossing is physics. If you hit a coin at the same point with the same force, it does the same thing. Of course it does. So let me do one sentence of the physics, and then I'll turn it over to a real physicist. So coin tossing is physics, okay. This is a simplified model of physics, but the point is most clearly made here. When the coin leaves my hand, it has a speed, how fast is it going, and it has a rate of spin. How fast, how many times a second is it turning over? Okay? If you knew how fast it was going and how many times a second it's turning over, Newton tells you when it will land. And if you know when it will land, how long it will take to land, you know how many times it turned over. So there is the phase portrait of this, as we call it. There's a velocity, spin. Those are the two initial conditions. And every flip of the coin corresponds to a dot on this picture. How fast it's going and how many times a second is it turning. I should use Daniel's gadget or somebody's gadget. I'll see if I can do this without blinding me. Take that kind of a spin. So that's a spin of the coin which has pretty high velocity. It's far over this way from zero, but the omega is very small. So the coin is going up like a pizza, and it doesn't turn over, right? There are those kind of, right? It's going up very fast, but doesn't have a lot of this. Right? Okay, so there's a region in the velocity spin plane where the coin doesn't turn over at all. And then there's a region where the coin turns over once, and a region where the coin turns over twice. Let me show you what those look like better. That's the real picture from a paper by Joe Keller. So one thing you can see from this picture, if you don't hypnotize yourself, is as you go away from zero, small changes in initial conditions make for the difference between heads and tails. Okay? That's right, and of course that is behind the randomness of coin tossing when real people do it. But I wanted to know, when real people flip real coins, where are we on that picture? Okay, that's another question. Are we down there where it's not very random, or are we off in Never Never Land? So I love talking about this because you guys have ideas. So I need to know two things. When I do that, how fast is it going, and how many times? It's not so easy to think about. Okay, so how fast is it going? Not so bad. Have a friend with a stopwatch. 1, 2, 3, flip. And after an hour or two, you have some data, and you can tell how long does it take to go up, and you can convert that into how fast is it going. And a 1 foot flip takes about half a second. Okay. Now, how many times a second is it turning? That's harder. My first idea is I would go get, this is 20 years ago, I would go get a high-speed slow-motion camera and just be able to film it and figure it out. Well, at Stanford at that time, there was one high-speed slow-motion camera, which was owned by the football team. And there was a 1 week slot in the summer when they would let me look at it, but I had to hire their operator, and it was going to be $2,000 an hour. And I wanted to know, but I didn't want to know that badly. So I had my first good idea, which is this idea. Here's a piece of experimental material here. I took a coin, okay, and I attached a piece of this plastic dental floss that flattens out. So that's flat now. The coin's heads up. I do that, friend times it, and then I unwrap the coin so I know how many times it turned. High tech, high tech. The summary of my findings. No, but I mean, it's at least a piece of an idea. Okay, the summary of my findings are a 1 foot flip takes about half a second. The coin's going up about 5.5 miles an hour. Using a tunable strobe, I didn't tell you that story, but I also tried that, and the coin and the ribbon. A typical coin toss is doing something between 15 and 20 revolutions. And when you go through and look back at this picture and ask, where are we on the picture? Well, there's two things. In velocity space, how far are we away? It's a fifth. Oh, so here's 5, here's 1, a fifth. It's pretty close to 0. But it's 40 units up in spin space. So this picture says nothing about tossing real coins. But the math behind the picture tells you how serrated things are in that region. And there's a real sense in which coin tossing the way we normally do it is fair to 2 decimal places, but not to 3. That is, Susan and I and Richard Montgomery did a much more sophisticated analysis and concluded it was about 0.51 for the coin to come up the same way it started. So, and every year when the Super Bowl comes around, I get a call from ESPN saying, wouldn't I do a minute on the randomness of the coin toss? Okay. That's my introduction. Okay, that's coin tossing, the beginning. Okay.
I'm actually going to start also on coin tossing just with one view graph. Now, I have friends, actually they're some of Persi's friends too, who can do very, very clever experiments and design them very, very precisely so everything works very, very well. And so one thing which one can imagine is saying, look, I want a coin toss that will work much better. I don't really want to just have something turn over a measly 20 times. I really want it to turn over as many times until it gets more and more random, or it looks more and more random if you turn it an enormous number of times. So I said, okay, I really want one that turns 100,000 times. So they'll first say, well, I'm sort of crazy, but then I'll say, wait a minute, do you really care if it goes up? And I say, well, I don't really care if it goes up. I want it to turn a lot of times. So maybe they'd say, well, let me string it across something. So let me make it, I got a coin here suspended, and I'm just basically going to rotate it, and it could wiggle and go a bit more complicated. And then as it goes along here, depending on how many times it's turned around, it's up, down, there's an angle there. I'll see heads, tails, as a function of how hard I hit an issue, right? How hard I'm going to make it spin. So this is something where if I don't hit it quite right, so I want to hit it and then I want to hit it slightly differently, and then I look at this angle. Right? Eventually, of course, if it's up here, it's going to be heads. If it's down there, it's going to be tails. And look, I've hit it 2 times with very close to the same force. When I close, everything looks nice for a while, but once it's gone around many times, this one was heads and this one was tails, so I didn't do it quite right. Yes, that's exactly what Persi's Holdem might be coming to it quite well enough, things are sensitive to that, and the picture we showed here is really showing a lot of that sensitivity. If you're up here, you'll get it quite right over there, and you'll get it. Now, supposing, however, I have very clever friends, and maybe they'll get money from DARPA, and they can claim it's to do with making codes and so on. And so they want to make something which is really good pseudo-random number generator. It's almost random. They're cleverly enough that they know it's not really random, but anyone looking at it, even Persi, will think that it is. Okay. So they'll do it with 100,000 takes, and maybe we want to get 1% of the things predictable, so they need to be able to control the force to an accuracy of 10 parts per million, or 1 part in 10 million, so 10 to the minus 7 to get good enough predictability. So in principle, you could probably do this. If you spend a lot of money, you could do this. You could make a machine here that would touch the coins, and it would produce you something which is very close to random. Then you make a second machine. You know, and I want to do this to something. And you're going to do this to produce keywords that you're going to then use for a code, and you want to make those as pseudo-random as possible, so Persi's friends can't dig into them. So you make them so that if I tell you that I'm going to set my initial force at 1.87543, okay, the other guy sets his machine at 1.78543, whatever I said, it'll be heads, but if I set it at 1.24897, it'll be tails. Okay? So what I'm going to do is I'm going to tell the guy far away what I set the number at. And he's going to be able to do exactly the same and produce the heads or tails. I'll do this lots of times. I can produce some code words that he can feed into his code and make it much less hard to break. So I do this and I test my machine very, very carefully and find that I really can do this well enough for it to be useful. So then what I do is I send this machine off to my friend, and he puts it in the bottom of Cheyenne Mountain, where they control nuclear weapons and things from. And I send him a bunch of numbers, and he does it, and he gets out complete nonsense. And he gets stuff he can't decode at all. There's something wrong. I go there, I check the machine. Everything seems to be fine. Okay. Well, what happened? What happened is that with something, if you try to make it this good, you have to be more and more careful as to what things it depends on. So we put all kinds of anti-vibration things on this so the trucks going by doesn't mess things up, okay? But some things we can't control, like the fact that Stanford's building some building over there. That building, the gravity is different yesterday than it was the day before. And it's different today because there's gravitational force in that building. Or some people in the next room. Or what's the fact that I got a mountain above me, not a mountain above me. Okay? And you can very easily estimate that by the time you get something that's trying to be this good, the forces that you don't know anything about coming from outside the room, and you get an earthquake, we don't vibrate from it, but it changes the gravity around, that's enough to mess this thing up. Okay, so this thing, I could do it in principle, but it's useless because the extra randomness are things I don't know about. Okay, and they may as well be random, I don't know anything about them. Okay, they really mess things up, and that's the problem is because physics works with continuous variables, right? They can have any action in principle versus computers which work with zeros and ones. Okay, and a lot of the difficulty in why you can break things is because computers work with zeros and ones and not things that are continuous. Okay. However, this thing, so this is very, very sensitive to exactly what forces I have than the other forces, and I can't really control things. However, it's not too bad. It's really the error, the amount of error I make sort of goes with the time. So if I said, okay, I'll make it 10,000 times, then I only have to be 10 times as accurate. If I make it 1,000,000 times, I'd have to be another 10 times more accurate and so on. Okay? And the reason why I could do this at all is because the error doesn't grow very rapidly as I make it go more and more times. Okay? So I can make it almost predictable because of that. Okay. But now I want to take another problem, and I want to start going towards things, at least to me, get more and more random because they get closer and closer to physics. Okay. Now I had a different misspent youth than Persi, and one of the games that I used to play was billiards. I never got anywhere near as good as Persi got with all kinds of games. But one of the things, a friend of mine I used to play billiards with, and he had what he called EDT, and that stood for eventual drop theory. And it was if you hit the balls hard enough, eventually something went in a pocket. Okay? So something was pretty random, but it turns out things are almost random, even if you just have one ball. Okay, if you've got a table with really good cushions and a really good ball, it'll bounce around for quite a long time. So let's ask what happens. I've got a ball bouncing around here. I've got a sort of oval a billiard. So I start over here. I've got this blue trajectory there. There's it goes around a bunch of times like this and then goes to there. Okay. Now I try to say, okay, there's a complicated trajectory. It's bound. I don't know what it is. It's got half a dozen bounces or so. Now I'm going to try to do it again. Okay, now I couldn't do this, but if I get someone who's really good at pool, they'll hit it and it gets very close. It's still close here. It gets close there. It gets close here. Wait a minute, now it's starting to get a little bit further apart. Now it's getting a little bit further apart. And by this point, it's a different half of the table. Okay, so no matter how good you are at pool, it gets harder and harder to do. And if you want to do a little better, then you can do it. If you want to make a machine, it'll do a bit better. Maybe it'll do 10 bounces instead of 6, and so on. Okay? And the reason is that if you look at the position here, they start off, then they get further away with time. And so, for example, whether I'm in the top half or the bottom half, after some point, I can't really control it. It sort of looks as if it's random. Okay? Now, this is actually very different than the case of the coin tossing. The coin tossing, I said, if you want to make it 10 times as good, okay, so you can go 10 times as long, then you really only have to make it your accuracy 10 times as good. Okay? But this one has the property that if I want to make it go 10 times as long, I have to make it incredibly much better. Okay? More like 10 to the minus 10 times as good, or 10 to the 10 times as good. Okay? And the reason is that the errors here, the separation between the positions of the ball, say of the red try and of the blue try, they'll initially be very small, but then they'll grow, and then of course eventually they can't get too big because the table's bounded. Okay? Well, that doesn't look that different. Sort of linear in time would be like this, as the errors one got from the coin tossing. Okay? But if I plot this in a way that's more careful, and so I do my experiments very carefully, and then what I'm going to do now, I'm going to plot the separation again, and I'm now going to plot it over a very big range. Okay, so I'm going to plot it, goes 10 to the minus 5 down here, up to 1 as a fraction of the size of the table. And if you started them very close together initially, you would find no matter how close you got close initially, they would sort of wiggle around the difference, but it would grow here, and it would go exponentially. So the separation between them would grow exponentially. After some time here, it's gone 10 to the minus 3, 10 to the minus 1, and so on. Okay? So what this means, if I started down incredibly good, I started down at 10 to the minus 8. Okay, I started incredibly good, way down here. It would only take about twice as long before it looked completely random. Okay? So this is something which depends on exponentially on how well you can control it. Okay, this is the ideal billiard. Okay, there's no friction, there's no one walking around the room, and so on. This is even in principle as to what happens in this game with just one billiard ball in it. The separation goes exponentially in time. Okay. Now, this is something which is a manifestation, in fact, in many ways, is the crucial feature of chaos. Okay, now, chaos is a term that gets misused all over the place. There's a pretty well-defined sense of chaos, at least the physicists will use. And chaotic dynamics is dynamics where how things change. So if you start with two things that are almost the same, and then you do two experiments that are as close to identical as you can, and let them go, that the error, or the separation between the two trajectories, in the billiard ball, we see what we mean by trajectories, but generally that will go exponentially with time. The longer you go, the more the errors will get, and of course at some point they saturate, and if you do smaller and smaller, do better and better, they'll still grow. It won't take much longer before it's hopeless. And this is often known as the butterfly effect. It's that a butterfly flaps its wings, and a few weeks later, that affects the weather. Okay, like where a thunderstorm is. On even longer time scales, it affects things which are closer to things like climate, or at least some aspects of that. And so it's something which, the tiny little things can have very big effect if I wait long enough. And I don't have to wait very long. I mean, it's a few weeks is sort of the right time scale where it starts making a difference. Okay? So what does this mean? This means if I wait a very long time between when I make measurements, say this billiard ball bouncing around, it's pretty close to random. Okay, it's about as close to random as things that one can reasonably get. So for example, I could take this and I could say, okay, every 100 bounces. Okay, I can make it so my billiard ball is frictionless, or I can do something to keep it going a bit. After every 100 bounces, I measure if it's in the top half, and if it is, I call it heads, or if in the bottom half, I call it tails, and I take that sequence after every 100 bounces. That's going to be pretty hard to tell that it's not random. Okay. If I did it every 10 bounces, certainly could, 20, 30, maybe 1,000, no way. Okay. So this is something which is really chaos, exponentially, and it's really sort of getting about as close to random as one reasonably can, still in a way which you can really study mathematically. You can set up physics things that are very close to that. Okay. So this is something which is very, very simple. This is just this one ball bouncing around, but it's one of the simplest examples of chaos, which comes in all sorts of systems, and is now very well understood, a lot of aspects of that. Okay. Now I'm a statistical mechanic. Statistical mechanic means that you like to play around a lot of things at once, but you don't really care exactly what they do. You just want to know in some average sense. Okay. So for example, if I want to tell you something about the air in this room, I could tell you where every single molecule is at this time. Okay, I couldn't really, because I don't have enough computer, this and so on. But even if I did, it wouldn't be very useful, right? It'd be some enormous strings of numbers, what would I do with it? But I can say some average things, like, there's about the same number over here, this half is over that half. And it's the ones over there are moving a bit faster than they are down here, and things like that. Okay. So how do I start thinking about statistical mechanics and sort of the randomness that comes in there in a crucial way, or the almost randomness? Well, then I'm going to have lots of particles. So I can think of doing that again with billiards. And this is now, say, when my friend's EDT starts coming in. So I have a lot of balls around here. They're bouncing around. They're little balls. They don't hit each other very much. They mostly hit into the walls. But I got a lot of them in here, so sort of things get random more easily. And the way they collide with each other makes it so that things get even more unpredictable. Okay. But I'm going to then ask a very simple statistical question, okay, which is like if you flip a coin many, many, many times, that you get roughly half heads, roughly half tails. But in fact, a given, if you throw it 100 times, you could get 60 and 40 and not be too upset by it. If you got 5 and 95, you might expect that Persi had done the coin flipping instead of me. Okay? And, but there's some sort of distribution there, which is called the binomial distribution, as to what one we get. Okay. So the sort of assumption is all these balls are bouncing around. They're not affecting each other too much. Which ones are in the top half and which ones in the bottom half are sort of independent of each other. And so what I can do is I can say, okay, each ball has about probably a half being in the bottom, half in the top. I can look at combinatoric factors, and I can end up with some result that tells me what the probability is that I'll find, say, h balls in the top and the rest of them in the bottom, n minus h in the bottom. Okay, so this is what the distribution is, and I can plot that. I can do a histogram. I can measure the probability here. I look at the probability here as a function of the number of I have n here, that's the maximum number, of course, 0 is the minimum number, and I'll find a histogram like this. And this is something which is very close to what's called a normal distribution, the bell-shaped distribution, the Gaussian distribution. It is that simple form here, and I've shown that in the green, and it's a very good approximation. It's characterized by a mean. The average here is just half n, half up, half in the top, half in the bottom, and a standard deviation, which is sort of the characteristic, what sort of typically how much things will deviate away from that. Okay, and that goes to square root of the number. So the bigger n is, the sort of sharper and sharper this gets. Okay. So these things occur all over the place, and they, very, very important, but they're not nearly as important as people that teach about them think. Okay, so I'm going to in particular show you a way in which they're very misleading. Okay. So one of the things I'm very interested in, and this comes up in a lot of times in evolution, so I'm interested in it, comes up a lot of times in physics and things, is not things like things that turn up heads, turn up tails, but it's things that rarely happen. They rarely happen, but if they sometimes happen, they can be very important, especially if they have big consequences. So I want to look at things that could potentially have some big consequences. Okay? So I'm going to particularly look at this thing with the balls, okay? And I'm going to start in a particular initial condition. I'm going to start with all the balls in one half. Okay, that's of course like a very rare configuration. So these can then move around for a while, and then I'll typically find this. I'll find about half of them in each. Not exactly, but roughly half in each. Okay? And I keep going, and I watch them, and I'll always have roughly half in each. I'll have some more, some less. But I'm not going to get back to this condition if I've got a lot of balls in there. Okay? So this is a phenomenon which gives rise to things that one's perception of the world is a lot of things irreversible. Right? If you spill a bucket on the ground, there's water all over the place. The water doesn't spontaneously come back into the bucket again. Okay, well, that's like this. I've started all in one place, and then they've spread around. Okay? But that's not really quite true. Okay, it's not really quite true. Okay? I'm now going to just show you a picture where I made some measurements. I didn't really make it, of course. I pretended to. I'm a theorist, so I'm good at pretend measurements. Okay? So I made some measurements here, and I looked as a function of time. Okay, and I measured the number of heads, and I was doing it wiggly. I was lazy. It's not an integer, but so the number that were in the top half is h. Okay, and it looked like this as a function of time. Okay, so you see it sort of wiggling around here. It's roughly the same, wiggling around, and over here it sort of deviates from that. Okay. Now, with during up and down, some people draw time going up, and some people draw time going down. Okay, so I want you to look at this picture and tell me which way was time. Which way was time going? Did I start here and then go that way, or did I start up here and go this way? So how many people think time is going up in this? Okay, how many people think that time is going down? Okay, how many people think that I'm a cheat? Only one. Persi didn't put up his hand. Okay. So I'm a cheat. Okay. I didn't tell you what I did. Okay, what I did is I started with a mixed around, so roughly half were in the top, half were in the bottom. But I started a very, very long time ago, and time is going this way. Okay? And then I said, I want to look at the time when the number of heads, the number in the top half, happens to hit some very large number. Okay? Maybe all of them in the top half, right? Over here. So what I did is I just waited. And I measured and measured and measured and waited. And then when I saw that, I stopped. And then I showed you just the last bit of the data because I couldn't show you all of it. Okay? However, you were correct. The right inference is that this goes that way, is that time goes that way, and this is one of the things one normal is. This is just analogous to waiting for all the water to come back into the bucket again. Okay, and I just waited until it happened, and then I showed you the picture of it coming back in the bucket of the movie of it. Okay, now of course I can't really do that with the water, but I can do it in some simple circumstances. Okay, so how would I do it? Well, what I would do is I would get my very clever experimentalist friends and get them to do, in principle, an experiment, which if they were willing to spend enough money, again, they could do. Well, I'm going to say, what are these balls? Well, I've got molecules bouncing around in the air. Okay, so I could use those as the balls. They're quite far apart. They don't hit each other very often, and so on. So I could do an experiment here where I looked at the molecules in air. Let's say I'm going to look at the water molecules in the air. They're a little easier to track, the water molecules. So I'm going to put a bit of air in a little container, and I'm going to have some water molecules in there in blue. They're going to bounce around, and then I'm going to count how many are in the top half, how many in the bottom half. The advantage of doing this is they can bounce around really fast. I can do my experiments really quickly, much faster than flipping coins. Okay? So what might I want to do here? Okay, well, I'm going to make a lot of measurements. And if I make this box, of water about 1/30th of a micron, these are going to bounce around here, and I can follow these. Okay? So now there's a bit I forgot to show. Okay, there we go. My other view graph. So I wanted to say, first is how many should I choose to put in that box? This is a crucial part, because if I'm going to get my experimentalists to do this, they're going to want to know how big the box should they make and so on. Okay. So this is exactly the question of how long do I have to wait, or would I guess, before all of them will come back into the top half if I started there. Okay. Eventually they will. There's some probability they will, but roughly how long would I have to wait? Well, roughly speaking, that's the sort of time scale it takes them to bounce around, times a number, which is just 1 over the probability they all in the top. Each one is probably a half, so this is just 2 to the n if I've got n balls. So my time I have to wait for is about 2 to the n. Okay. Now, if my bounce time is about a nanosecond, 10 to the minus 9 seconds, if n was 90, my recurrence time for them all to come into the top would be about the age of the universe. Okay, so my friend probably would not like me to tell him to do it with 90. Okay, 100, would have been a nice number, but you can't do that. But by the time I get down to 40, it's not totally unreasonable. At 40, the recurrence time at this rate would be about 10 cubed seconds, because 2 to the 40 is about 10 to the 12. Okay, so that's 1,000 seconds. I could do it during the lecture. Okay, and I would expect to see during the lecture, I would expect to maybe see a few times in which they were all in the top half. Okay. So I asked my friend to make this. Well, I haven't yet. I could ask him to make it, and then we can ask what happens. And now I seem to have randomly mixed up my view graphs. This is the most common kind of randomness that I encounter. So where is my correct one here? Where's it gone? So this. Okay, there it is. Okay. So here's my experiment I'm doing, and I'm doing this experiment, and I'm measuring them. And if I've got about 40. My volume I need, well, it's about 1/30th of a micron. I can make things this size. In principle, it's an experiment you could probably do. What I will find, of course, on average, I'll find 20 of them on the top. The standard deviation will be about 3. What does that mean? That means with 2 standard deviations away from that, so between 14 and 26, it'll happen about 95% of the time. Okay, so I'll get, if I do a histogram, I'll get something like this. And I could do this and I'd find it would look very nice. It would be pretty close to this bell curve, be very close to the binomial distribution. Everything will be very nice. But then I say, well, okay, I've done it lots of times, but I don't care about these boring things. I want to ask about all of it coming back into 1/2. I'm not going to see that very often. Okay? So then I can't plot it like this because I wouldn't be able to see it. So then I have to get him to do one of these plots, which is on a logarithmic scale, so I can see a lot more things. Okay? So what I would do then is I would tell him to plot it like this, and I would plot it so that the probability, fraction of the time, that I get a given h here is now on a big scale. So this is 1 in a trillion. 10 to the minus 12. Okay. So what do I know? Well, I know that the right answer is about 10 to the minus 12 here, and this blue curve is what the right answer is. That's what I would predict from the binomial distribution. Okay. Now, first thing you can ask is, what about this sort of Gaussian? I said it was pretty close to Gaussian. In fact, it is. A Gaussian is just a parabola on this scale. So a Gaussian, this normal distribution, works very, very well there, but you notice it stops working in here. Once I get far out, it stops working, and by the time I've got out to here, it's wrong by almost a factor of 1,000. So if I took this Gaussian distribution seriously, I would get my answer wrong by about 1,000. My experimental friend would get very upset, okay, because I told him it was going to happen 1 in 10 to the 9, it's really going to happen 1 in 10 to the 12. Okay, and he would sort of get upset by that. So I better do it better, and that's the danger, of course, of looking at Gaussians, and I'll say more about that in a minute. Okay. Now, if I actually do this, and I do this experiment with the 40 balls in the container I said, what I would actually find, this is a prediction, This is a prediction. Now, this is thinking about physics. I would find something that went like this, and actually, at some point, it would start deviating above this. It would actually deviate above the Gaussian. Then it would come down here, and when I got up to 40, it would actually be somewhere between the Gaussian and this. Okay? But it would actually be quite different by this point. Okay, by this point down here, it would be different from the predicted value from the binomial by about a factor of 50. Okay. Well, that's not as bad as a factor of 1,000, so it's a big enough factor that I would say, wait a minute, did I do the experiment right? Something else wrong? Is my physics assumptions wrong? Or whatever. Okay. Now, what's going on here, what the difference is some physics. There's extra physics in there. Okay. The water molecules are an ideal gas, but an ideal gas is almost ideal. It's never perfect in physics. So what I would have to do is I would try to look and say, well, what's going on? Is there something different that's happening over here or over there? Okay? And the answer is there is. If I look at this, I would find, say when I looked at the times when h was 24, so I've got more here, but not by a lot, they would be pretty randomly spaced around. But by the time I said I looked out here when h was 36, I would find they were pretty randomly spaced around. Of course, there's only a few over here. But you notice in the middle there's something in there. There's a whole bunch of them clumped together. Okay? This is the beginning of a raindrop. Okay, if I have too much water in the air in one place, so I just make too much water in the air, it starts forming raindrops. It forms condensation. Okay, and if I take typical humidity, well, not around here, but today happened to be a good day for doing this. So if I take the water today, I don't have to put too many times more than the average number of water molecules in before I start getting this. And the physics associated with that completely changes the behavior. With 40, it doesn't change it so much. This factor of 50, but by the time I did this with 60 in there, it would change it by a huge amount. But I can't really measure those. So there's a very important lesson here. Okay, the very important lesson is if you're interested in rare things, which one often is, you think rare things, what things being random, but random things are unlikely, like winning the lottery. Okay? Rare things, you have to be very careful there isn't something else that you didn't understand that you left out. Okay? You have to be careful that any things that people tell you, normal distribution, Gaussian things are beautifully bell-shaped, they tell you here, they tell you a lot of data, hit points here, they extrapolate and they get this green curve. That's way off. Okay, and then there's extra physics on this. Okay. So there's an importance lessons in this. There's several of them. Okay. The first one, and this is a very, very general one. It comes back to the question of why computers aren't useful for a lot of things. Computers are very good at interpolating. You make some model of something, you do a whole lot of things, you try it with different parameters, different conditions, and they're good at sort of interpolating. They can tell you what happens under normal conditions. Okay? That's how weather is forecast. Okay, sort of a range of things you've seen before. If you want to forecast climate 50 years from now, you have to extrapolate a lot. Okay? And extrapolation is always much, much harder. Okay? Here's a case where we're extrapolating. We were extrapolating from sort of knowing things in the middle. They worked fine. It was, okay, why shouldn't it work out all the way to the end? So when we get h of 40, when we have a anomalous number. And the reason it didn't is because something else comes in. We miss something. Okay? So extrapolation is very dangerous. And it's often done for these sort of statistical things. You measure the mean, you measure the variance. You say, okay, we understand it. It looks nice and bell-shaped, and we can understand what happens way out in the tail. Okay? That's almost always wrong. Okay? And it's very dangerous to do. The other one, which is assuming things are independent when they're really not. I assume that where each water molecule was independent of each other. Well, of course it's not right. They get in each other's way. That turns out it doesn't matter much. But they can all, the fact that they all kind of stick together, and once a few stick together, other ones start coming in if there are too many. That means they're not independent, right? They care about the sum already being there. Okay? So it means the thing I made initially, the assumption about one being in the bottom, whether another one's in the bottom or top doesn't matter. Okay, that's independent. They're sort of separately random. That's not true. The crucial thing here is that there were things in there that weren't independent. Okay, all the people in the room don't behave independently. Right? If a fire alarm went off, we would not behave independently as whether we stayed in here or left. Right? If the lecture just got boring, it may be more independent. Okay. So this is an important thing there. The other one, and this is also another very important lesson, is talking about probabilities of events that you've never seen. Okay, it's very dangerous. Okay, like the probability of something happening, like a building falling down spontaneously of a kind of building design no one's ever seen before. Right? No one ever used before. If you've seen that happen a few times, different sized earthquakes and things, you start saying, okay, we'll sort of believe that. But if people tell you that, oh, well, these range of earthquakes, the probability this building falls down is 1 in 100,000, you say, well, what do you mean by that? Right? Where did that number come from? Right? So you have to be very careful with talking about probability of events you've not yet seen. If you're looking at things all in the middle and you ask about the 40, you have to be very, very careful. Now, in these days, there's some interesting lessons here, and I as I said in the introduction, I used to be at Harvard, and I left it. That's a long story, which I won't go into. But while I was there, I got to know someone who's rather well, who's an economist. And there are, economists are a lot in the news these days, and particularly economists that didn't foresee that maybe there'd be problems like there have been. Okay? Now, Alan Greenspan has actually confessed to some sins. Okay? But there were two other people around the same time, actually, in the Clinton administration, who were involved in a lot of discussions and were in positions where they could have done something about whether they should allow lots of derivatives and all these complicated financial instruments, or whether they needed to regulate them. And they all agreed, or said separately, they shouldn't regulate these, and Bob Rubin and Larry Summers were the other two. And Larry Summers, for a while after this, was president of Harvard. Now, some of you may know of some infamous speech that Larry Summers gave, which, by the way, has nothing to do with why he was fired. It's public perception, that is, but actually has essentially nothing to do with it. And in this speech, you can disagree with everything he said, but there's one thing which everyone should disagree with. Okay? And there's a bit of it in there where he did some quantitative analysis. He's a famous mathematical economist, won all kinds of prizes and things. And he did a bit of analysis. Basically, he was trying to figure out what the chances are that you would have a male rather than a female that would end up being a math professor at a top university. Okay? And how he did this, he said he did about 20 different ways, and he always came up with the same answer. Okay? And I looked at this few paragraphs in the speech, and I said, oh my God, what has he done? Well, a former math colleague, David Mumford, a famous mathematician, saw this and immediately sent around emails to people saying, do you see this? And then the reporter from the Boston Globe called him, and he said that what Larry Summers had done was analogous to assuming that the world was flat. What he had done is he had taken something, which is distributions of IQs and various measures of mathematical ability and things, and looked at those, and you see they're beautifully Gaussian. They have a nice Gaussian. Then you assume you've got a shape of the Gaussian, and you assume you can extrapolate it all the way out to these rare things, which are people who end up math professors at top places. Okay. So he'd assumed the thing was exactly the same shape as you see near you. That's the same shape far away. That's, of course, like saying the Earth is flat. Okay. So it's an argument which is totally irrelevant. Okay. And this was not pointed out enough in the press. Okay. Now, what exactly the same thing has happened with, or very similar thing here, associated with financial problems. Okay. All of these derivatives, and everyone said, well, they're stabilizing. They make things more independent. They make things more. They look at everything. It fits nice models. But then, the things of where things very occasionally might happen, they get wrong, very wrong. Okay, and they do things a lot like assuming things are Gaussian when they're not, and you can show they're not. But that's assuming anything else gets too complicated. So we assume they're Gaussian. Okay? It's fine as long as everything's going normally, but there's very rare things which happen. Okay? And the other is assuming a lot of things are independent. They're not. Once someone starts panicking, other people start panicking as well. And things are very not independent, and everyone clumps up together, and we get this drop falls out, and things crash. Okay? So these are really rare, these rare things. One has to be really careful one has to be really careful of any kinds of extrapolations and sort of assumptions of independence. Okay? So the kind of things that way people use sort of the term randomness in everyday life, and economists who should know better, is often very, very misleading and is dangerous. So with a physicist, my answer to the question about whether things are really random is no, they're not. If you're really careful and you think about it enough, in a lot of physics situations, they may as well be random. Okay? But in a lot of other situations, particular ones that involve behavior of people or anything like that, then they're not. They may behave like in some things, but not in others, and it's very hard to extrapolate from that. Okay? So that's probably a good place to end. I'm just going to put this last slide up. Is does quantum mechanics matter? If anyone has any questions on that. Okay.
Okay, we have less than 10 minutes left for questions, and we do have another session immediately following this one. So if there are questions left over after our 10 minutes, we will adjourn outside to near the main entrance, and you can continue grilling our speakers at that location. But right now we have a few minutes for a few questions. Right there.
My question relates to this thing you just put up at the end. I mean, I was very surprised by the discussion. That when it started, I thought it was going to be about that. Einstein said, "Does God play dice with the universe?" And I think with the Bell's theorem experiments and so forth, my feeling is the answer is yes. God does play dice with the universe, and Einstein was wrong. But I know there's a lot of debate about that. There's quantum mechanical theories that are supposed to be able to be deterministic and so forth. And maybe to tie that into what you were talking about, I mean, if you take something like radioactive material decaying, it doesn't go click, click, click. It goes click, 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 click.
Yeah. Okay, so that's a very good question. It wasn't seeded. Okay, so for many things, some things quantum mechanics doesn't matter. Okay, quantum mechanics matters for chemistry. It makes molecules the way they are. It matters for determining interactions between water molecules. Okay, for almost all situations, as far as dynamics, chaos, things that look like randomness or whether they don't, quantum mechanics doesn't matter for, and classical is a very good approximation. Now, Einstein understood this. One of the main things he did was the theory of Brownian motion, which really is thinking about the random motion or apparent random motion of particles, of little particles. Okay? So for most purposes, quantum mechanics does not matter as far as randomness. However, you can do experiments, and these are real ones that people do. They're very, very difficult, where you really make things incredibly cold, incredibly cold, okay? And you incredibly well isolate them from environment. I mean, you have to do all kinds of amazing things to stop them interacting too much with other stuff. And then you can get into situations where the quantum randomness and things of the kind that you were referring to, where the randomness of quantum mechanics and all the weird things about quantum mechanics of how it doesn't really look sensible and in ways people don't understand, you can really start getting into even when you've got quite a few particles around. Traditionally, it's just one or two when you've got quite a few. Now, the specific question about radioactive decay, it turns out you can understand very well about radioactive decay and why that looks stochastic classically. And that's something which the quantum mechanical aspects of are, in fact, probably not very important.
Did you have a response?
Well, a brief one. People have tried to make random number generators based on radioactive decay. Very roughly, you have something like a rotary switch, which goes around 10,000 times a second. And when a Geiger counter blips, it stops. And so that should give you some sort of random stopping of the switch. And one of the problems in trying to harness quantum mechanics to make randomness is the physical interface. There's friction in the switch and all kinds of other problems, and when you actually try it versus theory, it doesn't work very well. And so that's just a practical observation, that it's been very hard to harness the assumed randomness in quantum mechanics. I'm not arguing about that, but to harness it to make real-world good random number generators.
And this, I mean, it's very related, and the reasons for that is because the quantum mechanics effects really become important when you can really isolate it from everything else. And of course, as soon as you try to use that quantum mechanics for doing something else, then you're getting back into big things and things are much more classical, things you can't control at all. And so those problems are not unrelated for those.
What are your, this might be my mind stretching really far out of the subject, but what are your ideas on coincidence?
Persi gives a whole lecture on coincidence.
What a coincidence.
The coincidence is psychology primarily.
Thanks for an easy question.
I think Persi's nodding. Persi's nodding his head. It's psychology. Humans are tremendously good at finding patterns, even when patterns aren't there. Okay. We're also, very good at finding when they are there, but we're also good at thinking they're there when they're not. Seeing animals in clouds. All kinds of things. And the coincidence is, almost entirely at least, related to the kind of things that we actually remember and notice, rather than actually things happening in a way that is what one thinks one is meaning when one says coincidence.
I agree. What's surprising is that we're surprised. But we are.
One question up there, yes.
That's also a psychology one, right? Is you're trying to figure out what the other person's brain is and what they're going through and so on. Okay. But however, I do have a story on this. Is a Russian physicist friend, Sasha Migdal. This is back in the days of those of you old enough. You remember the first programmable calculators, HP 25s, I think, and they had these, or 35s over there, where they were programmable. They had very, very simple programs you could put into them. Okay. So he made a program that would play just the even odds game, the simpler version than rock, paper, scissors on this calculator. Okay, with this incredibly tiny memory, incredibly tiny. It would beat almost everyone, 55, 60% of the time. Okay? Why? Because people are very, very bad at picking numbers that are random. The best you can do in that game, or at least the least bad you can do, especially on a computer, is to pick numbers completely randomly. That's very hard to do, and the computer can see patterns in how you're picking numbers that it can take advantage of, even with incredibly simple computer program incredibly simple. And so this is one of the things which is, I mean, it's again related to the fact that we sort of see things as coincidences. We're very bad at recognizing things as whether they're random or not and generating them or not. Okay, but basically, those games are a matter of psychology, or seeing the patterns in what your opponent is doing.
Okay, time for one more question. Here in front, or halfway back, yes.
I remain confused about what, I'm sorry, listen carefully, what's random? I tried to imagine that any one of your collection of cards, some particular combination, I can't quite see where that fits in.
To a common language conception of randomness.
Possibilities. To say that it's random means that there's.
Well, what I mean by saying it's random, I can at least answer that. I can't answer what you mean by saying it's random, but what I mean by saying it's random is that I believe that all outcomes are approximately equally likely. And that what it means to say I believe is I'd make small bets on any reasonable question about that. So that's a sort of pragmatic answer to what I mean by random. That is, in card shuffling, all of the different possible outcomes with, say, a deck of 4 cards, if they were well shuffled, each of the 24 different outcomes is approximately likely. And what I mean by that is that I believe that and act on it. But that's so I'm a subjectivist, and I think randomness is a statement about us and not about the universe.
Okay, it is now 2:30, so let's have a non-random round of applause for our speakers. Thank you. And you'll have to pick up all of your papers.
I think I have all mine, yes.
And I want to ask that people who are in rows where there are